Hello, I'm Julian Dolby from IBM Research, and I'm here to tell you about Wala using GNU taint analysis. In Chinese mythology, GNU is a weaver goddess, and GNU taint analysis is going to weave together different IDEs, languages, and analysis components for taint analysis. In the legends, GNU was a user of the Magpie Bridge, and GNU taint analysis is going to use Magpie Bridge as well. Rather than define taint analysis for SOAP, I'm simply going to go through some examples, and the first one is a Flask app written in Python, shown here in VS Code. The first thing the Flask app does is it reads the suggestion field from its request, and that is a source of tainted data because that's user input, and that's why it's shown with a yellow underscore. That tainted data request parameter is now passed to the inner and outer functions, which do some minor processing on them and return them. That's all shown with blue underscores because it's a tainted flow. And then that all part goes to subprocess.call there, which is where the data escapes the real world, hence it's a tainted sink, and so that is shown with a red underscore. Note that just above is another call to subprocess.call there. It even uses the same inner and outer functions to process its data, but it is passed a self-isolating string, so it is not and should not be shown as tainted. Note that this requires a little bit of context-sensitive data flow analysis to understand which call is actually tainted. The next example is HTML and Sublime. In this case, our tainted source is document.url, shown there on line 16, marked with a green underscore. That is then passed to the ID method, which is shown on line 6 there, just returns the same thing, which is then assigned to text and passed to document.write, where it's escapes to the web page, hence that is our tainted sink, and that so it's shown with a red underscore. Note there's another call there on line 19 to ID, but that's not a URL, so it should not be shown as tainted. And it has the same requirements for context-sensitive analysis as the Python example. Further note that the code that you see is actually in multiple script tags, and so the system must be able to assemble all of the JavaScript together in a sensible way to analyze it. And then note also that the first call on line 16 there uses the JavaScript function.call idiom, so the system needs to be able to understand at least that much JavaScript semantics. The next example is Android Java in Atom. This is an example from DroidBench. And particularly, you see a tainted sink at the top of the screen there, send text message, where data clearly escapes the real world. It is passed test1.method_b, and that calls the method on line 38 there, which calls a.f on its argument. We have enough type analysis in this example to understand that the call is to the method there in class B rather than class A. So we see our tainted source there, manager.getDevice ID. We return there on line 51, we return that to line 38 again, and then that gets returned to the tainted sink. Note that we need enough analysis to tell us that we're going to B and not A to get the tainted information correct. But maybe you don't want to use any of these new editors. It's also possible to use Emacs, and in this case I'm showing you JavaScript code, plain JavaScript this time, in Emacs. This is code you might see in Node.js, for example, although I'm using the same JavaScript code as last time, except that I added one more tainted source here in ID3.call. But to have the same analysis issues with understanding the reflective call and the context sensitivity required to tell which of these three calls is actually a tainted source. Note the labels you see on the edge there, the bottom of the screen. You have tainted flow step, tainted source, and tainted sink. Keep those in mind, they will come back. So I've tried to sketch a somewhat large space here. I showed you several IDEs, and of course there are many more. And I showed you several popular languages for taint analysis. And I tried to sketch some needs like context sensitivity to suggest, and type inference to suggest that the analysis needs some amount of machinery. But are we really going to build an analysis infrastructure with all the needed machinery for each of the languages we want to analyze, and then somehow integrate each of those into our IDEs? In a word, no. GNU is going to weave it all together. We have already seen from Linghui how we can use Magpie Bridge to support a variety of IDEs, and now we are going to see how to use the cross-language analysis framework Wala to analyze all of the different languages together. Wala was originally from IBM, and it's our cross-language framework. And in our case, it works by starting from existing tools to process source languages, which it converts into its common abstract syntax tree, or cast system. Once we have cast for a program, it is then converted into a more traditional IR that consists of control flow graphs, SSA, and the like. once we have a traditional IR, the core with IFDS, program dependence graph, system dependence graph, call graphs, and more, can operate on all of those languages together, and it's all supported by a rich set of utilities, including a graph. In particular, we are going to use graph reachability to do taint analysis. We start with a graph there. That's Waller's graph idiom, called G. And then once we have the graph, the first thing we do is we walk across the nodes of the graph to see which ones are endpoints, are sources of tainted data. For each one that's a source, we create a BFS for Pathfinder, which is Waller's utility for looking for shortest paths across a graph, looking for paths that flow to sinks of tainted data. As we find such paths, we gather them into a list and return them. So we're going to use graph reachability, but of course we need a graph. And this is a driver. This is a piece of code that would be called potentially by a Magpie bridge. And the first thing we need to do is make a call graph builder. The AST SSA propagation call graph builder is Waller's abstract class that represents call graph builders for all the different languages we support. So this piece of code is going to be completely cross-language, although make builder will obviously be specified per language. Once we have the builder, we build a call graph, and then we build a system dependence graph, or SDG. That's a graph of statements, where statement is the idiom for Waller's IR nodes in an SDG. The graph is completely language neutral, except for any specialization of modref needed by a particular language. Once we have the SDG, that is what we give to the graph reachability code on the previous slide, along with the source finder and sink finder that we need, and that gives us all the paths we need, and then we'll see what to do with them next. But let's look at the components of this system. The first thing we needed was a source finder. In this case, we're looking for the sources are normal statements, and in particular, they're normal statements. They're read statements reading a field called URL. Remember that in JavaScript, document.url was our tainted source. The sink finder is looking for param callee, which is the Waller idiom for arguments to methods in the SDG. And in particular, it's looking for arguments to the method document.prototype.write, which is our tainted sink. In this case, Waller has a lot of support for modref of all the different languages we support, and so we can just use the standard JavaScript one without any further requirements. But those are those components we need, but I had said before, we also need a call graph. And if we're going to support multiple languages, we clearly need different call graph builders for the different languages. I'm going to start with the HTML one. In this case, what we do is we get one file from Magpie Bridge, which will be the web page that we are analyzing. And then we pass it to the HTML CG builder in Waller, which basically takes a web page, extracts the JavaScript code, builds a model of the DOM, analyzes the entire thing, and returns it. So that's where we got our path. But now we have the paths. What do we do with it? Well, for each path, what we do is we go through each node in the path, each step along the way, and we create an analysis result object for it. And these you saw these before in the English talk. This is how we communicate the results of the analysis back to Magpie Bridge. And for each step in the path, we're simply computing those messages that you had seen on the slides: tainted sink, tainted source, and tainted flow step. That's where this is the code that produces the messages that you saw on the screenshots. And with that, you see the whole thing, how we can take our programs and do taint analysis across all of them in no language, in a systems independent sort of way. And with that, I've come to the end of the presentation. Thank you. I hope you have seen how we can use GNU to weave together all the different IDEs, languages, and analysis components to build taint analysis. Check out the websites, and where you can see all of the code that makes all of this beyond what I showed you on these slides. With that, thank you for your attention.
Thank you very much, Julian, for closing with a talk that weaves together many of the discussions that we've had before. And yet, of course, we now have the opportunity to ask Julian a couple of questions before we go to our closing and the announcement of the Best Presentation Award for the three scientific papers. But let's start with questions for Julian and or for Voila. Does anyone have any questions to pose? So I'm not seeing any concrete questions yet. Let's give it a minute. Maybe I can ask a question. So the CAST framework that you have for taking in input for different languages, what assumptions does it make about the language? Or put another way, what languages would be very difficult for you to support if I now wanted to go ahead and support them?
Can you hear me?
Yes, we can hear you now.
Okay, good. We mostly have worked on what I would loosely call Java-like languages. Well, not really Java-like. Python, JavaScript, Java have been the language we've used the most. We also are using HTML, but basically any language that can generate a reasonably normal, conventional-looking abstract syntax tree where you would have, statements of different kinds. It could be functional, it could be imperative, it could be object-oriented, it could be whatever. You have methods, you might typically have classes or functions, that sort of thing. Any language that is broadly in that class. And also any language, ideally what we use is languages for which there's an existing tool that gives us some form of AST that we can then convert to CAST fairly easily.
Okay, that sounds fairly general. Thank you. Then we have two audience questions. Manas Thakur from IIT Mandi says, nice talk. Does Voila handle reflection in Java programs?
So the short answer is yes. So then let me give you a slightly longer answer, which is, in general, handling reflection is an open-ended and not very solvable problem. That is, if I read a string from standard input and I pass it to class.forename, there is nothing in the code that gives me any insight about what that string is, although we do several things. There's a bunch of analysis that when we have processing done to strings, we may have some estimate of what the string is. We can sometimes use that. The other thing we've taken other approaches where, for instance, someone uses reflection. They usually then take the type, the thing they created, and they cast it to some type. We have a mode where you assume that those sorts of casts succeed, and from that you infer the kinds of types you must have created. And we have support for things like if you have a class and you call get method on it, if those strings are reasonably constant, then we can figure out what the method is, right? Basically, anytime we have static information we can use, there's typically a way to use it. Although, of course, there's nothing you can do sometimes.
Thank you. Next question is Ansuman Dulia, IIT Bombay. How does Voila assist in defining taint sources, taint sinks, and so on in a language/application independent way?
Okay, so let's step back a moment. So there's a level in which it doesn't make a lot of sense to define a taint source in a language independent way, because the kinds of constructs that are your sources are somewhat dependent on your language. So if you remember from my slide with the source finder and the sink finder, that was basically looking at the system dependence graph and just asking, is this a statement that reads document.url? So that is the kind of sink and source that we support. And that is we actually use exactly the same interface there. That was JavaScript you saw, but Python and Java are exactly the same interface, although obviously the particular functions are different. In Flask, subprocess.call was a sink. And in JavaScript, it was document.prototype.write. But they're both function calls, and in both cases, you're looking for arguments to those function calls. And so to that extent, the sink definition is exactly the same.
Thank you. Then we have Joana Cecilia da Silva Santos from Rochester Institute of Technology. For Java applications, does Voila have a way to handle the program's dependencies, for instance, by supporting pom.xml files directly?
So Voila typically works by being given a program scope. Now, we just heard in Ninghui's talk how Magpie Bridge project services are particularly able to handle pom.xml and extract the dependencies. So in that case, what would happen is that code would give from the IDE, it would find the pom.xml, it would figure out what the scope is, and it would hand all of that information to Voila, which would then build a program scope out of it. So the short answer is Voila itself expects a program graph, a program scope to be defined, but tools like Magpie Bridge, on which I also work, can assemble one for you for many popular kinds of things like Maven, Gradle, Eclipse, that sort of thing.
Thank you very much. That seems to be the extent of the questions so far. Then, Julian, thank you again for the talk and for answering the various and varied questions.